Hi everyone, I hope this is going to be a short video. This statement you can see here sounds very strong, but I need to communicate this message. I think this is important at this moment. In biology, it's perhaps very difficult to say something very strong because for any single process in physical process in cellular biology, multiple scenario can happen, so there is always some exception. But yeah, let's talk about this. Let's talk about the virus cell fusion process. I talked about these things in other videos, but I think I need to draw and say something here. So say this is the virus and this is the cell membrane. And virus contains some spike proteins. So the way I understand the variant is that perhaps the virus can have slightly different structure in the spike protein, maybe in the cell membrane, some of the proteins in the cell membrane, or even RNA inside the virus. So there may have different construction, slightly different, and the mutation is always happening in our body, especially for the virus. So I'll talk about this, why we should not be worried about virus mutation. But let's first talk about the virus fusion process. So most of the study I found that were concerned about when it is talking about cell membrane fusion, those literature concerned about spike protein and the cell receptor and the construction of spike protein, different kind of domain of the spike protein and things like that. So I think this is very well established by now, like what plays the role here to make a fusion process. But what has not been discussed extensively, or maybe didn't talk about yet, about the virus cell fusion pore expansion mechanism. So once this makes a fusion, it starts a fusion, that's not the end of the story. So let me redraw a little bit here. Let me make it a very close. So let's think about this as the starting of the cell membrane fusion process. So when it starts, it makes a pore. When it makes a pore, the viral RNA goes into the cell through the cell membrane. But as I said, this is not the end of the story. So let me draw again. Say it's just started the fusion process. This is the membrane. Sorry for the bad drawing. And the viral RNA and the spike protein here. So what can happen is that the cell, based on the cell membrane tension differences between cell, this is the cell part and this is the virus membrane. If there is a cell membrane difference between virus and cell, then the dynamics of this fusion pore expansion will be changed. So for one certain case, there will have two different cases that is explained in this article here. And I took this image from this article, and there could have either of the two different scenarios. In one scenario, let's talk about this scenario first. So what happened when the membrane tension of the virus is higher, like this is higher than the membrane tension of the cell, this one and this one, what will happen let me draw another picture, little bit bigger. So this is the cell membrane tension, virus membrane tension, and this is the cell membrane tension. So when fusion starts, the pore generally expands in this way and this way. So all the liquids kind of goes this way and this way. But if the cell membrane, virus membrane tension is higher than the cell membrane tension, then there is a kind of, the membrane is kind of, there is a flow going on in this membrane. So the higher tension will pull the lower tension cell membrane. In that scenario, there will some fluid flow in the opposite direction. So when this happens, actually this expansion stops. When this expansion stops, everything inside the virus membrane is driven like this. So in that scenario, the viral RNA will go farther away from the cell membrane. But if the cell membrane tension and virus membrane tension is the same, in that case it will continue to grow like this, because there is no pulling force in the virus membrane. In that case, this will happen. So virus RNA will reside next to the cell membrane. And even if the cell membrane tension is much higher, then again same thing will happen. I'm not going to discuss all these details. We have talked about this here. But the idea is there is a critical membrane tension difference between virus and cell membrane for which this will happen. When this happens in the cell, then the cell replication machinery will easily grab the viral RNA and will make another copy of it. But when this happens, there is a membrane, there is a interaction between cell membrane and the viral RNA. So it will not easily be picked up, the viral RNA, easily be picked up by the cell membrane, by the replication machinery. So in that case, it can be like through budding process, it can make another copy of the, it can just form another virus, or in the cell, some protein can destroy the RNA. So the chances of getting another copy of the virus or multiple copy of the virus is very low for this scenario. But when this happens, the chances of getting viral, the replicated virus, multiple copies maybe, is much higher for this one. So when this can happen? This can happen when there are many other ways to do this for this kind of changes, membrane tension differences. But one major thing is the temperature differences. If the temperature change means if it becomes cold. So say this is the mucus layer, and say this is the nasal airway, and this is the part of the cell, endothelial cell, and virus is attached to the cell membrane, and this is the mucous layer. So when air comes in, because of the cold air and also depending on the humidity, it will control the temperature of this mucous layer. And when temperature drops, the membrane tension builds up, and there is a critical membrane tension difference for which virus will go like this, and it will replicate within a moment. So I talked in another videos all the details, but the point here is that when there is some kind of like variance, say some spike protein, that there is some changes in the spike protein, or maybe changes in the membrane structure. So what can happen is that the property of the virus will be changed slightly. So depending on the temperature, the critical membranation difference can happen at a slightly changed temperature. So for example, this can happen, I don't know, I'm just guessing, say 31 degrees Celsius. Maybe in another viral variant, this can happen maybe 30 degrees Celsius or maybe 31.5 degrees Celsius. So this can happen a slight changes of the temperature if this has happened. So that is the only issue when you have the variants. But if it changes the RNA, then and if it does something inside the cell, then I cannot tell what can happen, and that's, I think, is not my I don't have much idea about this. So I think in that case you can consider it's a different virus. But when there is a slight changes and virus mutates all the time, I don't think that really can be an issue other than a slight changes of this critical membrane tension difference. So how the critical membrane tension difference happens? It can happen through inhaling air. So our nasal airway is generally lower than our body temperature, and at lower temperature the membrane tension builds up, and at there is some critical temperature for which this can happen, and that can make much more replication, and that can make people sick. So that's I tested, I checked the weather data in USA, and I'll show quickly what I got. So I talked about this slide previously, but briefly I'll talk about, I mean, in another video on my YouTube channel, but briefly I'll talk about this because this is very, very important. So I collected weather data for this period. You can see from August 20th to December 20th. You can look carefully on all of this data. So I got the outdoor, I measured outdoor wet bulb temperature, and from outdoor temperature and dew point temperature, basically it contains the data for humidity. So temperature and humidity makes the wet bulb temperature. So I calculated wet bulb temperature for each of the US counties. Then I calculated indoor wet bulb temperature. So how I did that, we published a preprint. You can go over this literature and you'll learn how we calculated it. But what we got is that so we got so many data points, and then we just took those data for 9 days period of time when indoor wet bulb temperature did not change significantly. Say standard deviation is less than 0.6. So those data was plotted here, and you can see that we have a kind of critical wet bulb temperature for which virus, the infection or the virus cases grows much higher. When it goes below like less than 10 or 11, you see the number of cases goes lower, and when it goes higher, it also goes higher too. So we got roughly 11 to 13 or 14. 11 to 14 is a sort of temperature at which virus grows much faster. Because of it's a kind of statistical analysis, that's why we cannot exactly pinpoint what are those temperature for each point, but still we can get a rough idea that 11 to 14 degrees Celsius is much virus infectious temperature. And when it goes to more than 14 degrees Celsius indoor wet bulb temperature, we did not see much cases. Especially we didn't find any single county that reported more than 100 cases per 100K population. So this is really, really significant. That means when indoor wet bulb temperature goes higher than 14 degrees Celsius, number of cases goes low. That means when our nasal airway temperature becomes higher, that kind of fusion process that I talked earlier was much lower. So if there is some variance, maybe some virus variant, the critical temperature is here, maybe other variant is here, maybe another different variant can have this one. So depending on different variant, you can have slightly different critical indoor wet bulb temperature. So that's what I wanted to say here. Let's move on to the next slide. So I wanted to talk about this plot. You can see this plot and this one. This is from December 3 to December 11, and this is from October 15 to October 23. So what I did from all the data points during this time, from so many different counties, I took the indoor wet bulb temperature, which did not vary much, so standard deviation is less than 1, so that I can pinpoint which temperature causes what, how many cases per 100K population. So for this time period, I found that roughly around 11.5 degrees Celsius was the most infectious, like it causes around 900 cases per 100K population. So during that time, it happened somewhere here, somewhere here, somewhere here. This is the red dot here. The count is here. And when during December 3 to December 11, the most infectious type temperature, I found that it's roughly around 13 degrees Celsius. And this happened in this zone, basically, like somewhere in Tennessee and other region here. So these two temperature represent two different variants? I don't know. It could be, or maybe depending on the weather, their preference of indoor temperature could be different. So the way I got indoor wet bulb temperature is that I considered that everyone stay at 21 degrees Celsius indoor temperature, and I calculated indoor humidity from outdoor humidity, and then I calculated the indoor wet bulb temperature. But from this analysis, it sounds like perhaps in this time there is one virus was dominant. Perhaps in this time another virus was like this, another mutant virus was dominant in these areas and in this time frame. So it really doesn't matter that much. It matters when it always related to some kind of cold environment. You see it's 13 and 11.5. It really doesn't make too much differences. That's why I considered this as a kind of 11 to 14 degrees Celsius, or maybe 10 to 14 is a kind of infectious temperature. But some variant could be at 13 degrees Celsius, and some could be at 11.5, and things like that. So that's what I mean by the variant. So it's not really a significant issue for me. It's all what is happening is the weather. If we understand how weather plays the role here, then I think we can save ourselves. Okay, let's move on to the next. So this is my final slide. I wanted to make it very short, but yeah, unfortunately I couldn't make it. Already 20 minutes gone. So I tweeted this picture other day on April 21, and I mentioned that the cases in Michigan is going down because of this scenario. So this is the infectious temperature zone, 11 to 14 degrees Celsius. When indoor wet bulb temperature goes higher than that, that means people are not getting sick enough, and number of cases going down. And you can see that the indoor wet bulb temperature goes higher than 14 degrees Celsius, and you can clearly see from here. And outdoor also, generally outdoor remains infectious when it's around 5 degrees Celsius. When it goes high, it doesn't really remain infectious, like even though it seems like in the infectious zone, but when outdoor it's infectious when you're indoor. This is indoor, but in outdoor perhaps we are on a moving scenario, not on a rest scenario, so our breathing pattern change. Also we may have mask, so both it dictates that this is not infectious regime. That's why cases drop significantly. And on this day, I said that while cases went down, the next few days it may stay wherever the latest day, like it will stay here, or it may go up, or maybe stay here. And you can see last few days, because of this infectious temperature zone, it stays roughly as in the same spot. It goes slightly down, but I think it makes sense what I meant by this. So we can get a very good indication how we can lower the cases, or maybe how we can stop the number of cases. So say how many days here goes out of this infectious zone. So I can see 1, 2, 3, 4, 5, 6, perhaps 6 consecutive days. The temperature goes up and down, like it's the dot represents the mean temperature, but it sometimes of the day it goes to the infectious zone, sometimes it goes out. So overall you can see there is a negative effect on the COVID. So if we can continuously do the same kind of scenario, let's say for 10 days, the cases will significantly go down. And there are multiple ways to do that. For example, what I do, every day I take shower for maybe 30 minutes with hot water. And what happens when I take shower, my toilet becomes very hot and humid. The indoor wet bulb temperature goes way higher than 14, so it's kind of 18 degrees Celsius or 19 degrees Celsius. So if we can do every day, if all people can do every day, then that's one way. Another way is you can wear mask indoor, then your nasal airway temperature will go up, and it will save. Another way could be maybe you can inhale steam, hot steam or warm steam occasionally. Sometimes that can be another way. Another way could be living in a small room with multiple people. What happens if you live in a small room or a small house with multiple people, the room wet bulb temperature automatically goes up. So there are ways to reduce the number of cases, and also you can make yourself safe. I'm sorry I couldn't make a very formal video. Actually, I have to do these days a lot of things. Even I cannot cross-check what I told, and so please forgive my very informal videos, and if I have mistakes, please forgive me. And I have multiple videos. If something doesn't make sense, you can watch those. And yeah, if you think that these videos are helpful, please share with other people so that everyone can get benefited here. And again, sorry, I wanted to make it short, but it becomes so long. Thank you for your attention.